say
Hi.
hi. Yeah, everyone says hello to
Good luck
Brandon
at
and
debate.
Sherry. Yeah, good
Have
luck
fun.
good luck at Iowa. Wow. All right. Well, I bet you guys are happy to watch this video. I'm sure you're here in Iowa, eager to watch this better than TV. Let me tell you. Wow, what fun. Okay, so yeah, we're looking at line integrals. You know what? Yesterday we were dealing with line integrals where we had conservative vector fields. Hey, those are cool. Plug in your beginning and ending points, and hey, you're done. You just subtract the function evaluated at those points. And if we ever had an enclosed path, that line integral was 0. But let's face it, that's a little contrived. Who's to say that the function that we're working with, that we're going to have a conservative vector field, that f, the vector field, would be equivalent to a gradient function? You know, very often that doesn't happen. So today we learned the relationship between a line integral around a simple closed curve. Everything will be simple and closed. And a double integral over the plane. There is a connection. And wow, that can be phenomenally helpful. I hope you're going to agree with that. Let's very quickly take a look at Green's theorem, which we'll address in a moment. But you have to have curves that have positive orientation. Positive orientation. Think back to trig when we measured an angle. If an angle was measured in a positive direction, we moved what direction? Counterclockwise, right? Counterclockwise. And if you look at these examples, you could see, well, maybe not as clearly, that when the arrow is moving in a counterclockwise direction, we are going to be called positive orientation. Likewise, if we were moving clockwise, then we would have negative orientation. And another way some authors explain it is if you're moving in a positive orientation, if a person was moving around the curve, their left side, their left arm and their left leg would always be pointing within to the area that's enclosed. Okay? So that's first and foremost. Green's theorem doesn't work if we don't have that direction. It's very specific. But what does Green's theorem say? Let C be a positively oriented, piecewise smooth, simply closed curve in the plane. And let's say that D is the region bounded by C. If P and Q have continuous partial derivatives on an open interval that contains D, then, my goodness, look at this. The line integral evaluated of P dx plus Q dy would be equal to the double integral that we studied last chapter of the double integral over some region D. By the way, the D region that's enclosed by that curve. But look, that would be in the integrand partial derivative of Q with respect to x minus the partial derivative of P with respect to y. And that is an amazing connection, an absolutely amazing connection. One other thing that I think we need to talk about, sometimes they will give you specific information that will say, hey, your path is going counterclockwise, therefore it has positive orientation. Another notation that we're going to see to indicate positive orientation is this symbol right here. It almost looks like a little ring going around the integral. Looks like a little ring. That's saying positive orientation. And this is not 100% conventional. Sometimes, you can even look in some textbooks, and they'll even put a arrow that would seem to indicate that you're moving counterclockwise. But you see that little ring, or you see the little ring with the arrow, that means, hey, I'm going in a positive orientation. It means, hey, if I'm enclosing a region, maybe, just maybe, I can use Green's theorem. So what's the power of Green's theorem? Let's look back to a problem that you would have been doing last week. A couple of sections ago, we learned how to evaluate line integrals. And my goodness, here would be the quandary. Not that this would be a difficult problem. This would be a very tedious and long one. Look, it says evaluate that line integral of x to the 4 dx plus xy dy. C is the triangular curve consisting of line segments. So let's go ahead and just draw out our curve C. We'd go from 0, 0 to 1 comma 0, from 1 comma 0 to 0 comma 1, and then from 0 comma 1 down to 0, 0. Notice that you don't have to start on the positive x axis. I think sometimes we almost think, oh, you must begin at 1 comma 0. No, you can begin anywhere. It's just notice that the motion that we're traveling is going to be in a counterclockwise fashion. That means we have positive orientation. It means we could use Green's theorem. Now, like I said before, you would have last week turned this into 3 separate problems. You would have had to set up 3 different parametrizations for each of those line segments, right? And you'd have to say, hey, what's x of t and what's y of t? And then we'd plug everything in, we'd integrate with the appropriate t-bounds. But we'd do those 3 separate pieces, and then we'd add them all together. Again, not super difficult, but then again, look at what the alternative is. The alternative, guys, is an amazing one. We'd say, well, we've got positive orientation. Let's go ahead and use Green's theorem. How? Well, Green's theorem says that we can integrate this over that enclosed region D. And here's my function P. Here's my function Q. P is whatever function is in front of dx with respect to dx. Q is the function with respect to y, with the dy. But Green's theorem is always going to reverse the trend, so to speak. We would take the partial derivative of Q with respect to x minus the partial derivative of P with respect to y. And what is the partial derivative of Q with respect to x? What would we get? Very simply just a y. And what about the partial derivative of P with respect to y? What's that? 0. Oh, that's nice, isn't it? So in other words, I'm saying, hey, let's go back to last chapter and say, could we evaluate that double integral, where of course we're integrating over D. Well, right now, rather than have to break this into 3 different parametrizations, all we have to do is say, well, now wait a minute, we could have a type 1 or a type 2 region. What do you think would be an easier approach? Well, honestly, I guess they're probably equally easy, wouldn't they? What might be a nice preference, though? Look at that. How about type 1? How about type 1? And if we've got type 1, we'd say, well, hey, we need boundaries for that vertical bar. We need to have equations for the boundaries of y. And very simply, look at this. We've got a line segment. Wow, remember our basic algebra, y equals mx plus b. I know what my b is. My b value is 1. How about my slope? I'm going to go down 1, right 1. So what's this equation? Y equals what? 1 minus x, or negative x plus 1, right? Fantastic. Fantastic. Look at this. Rather than having to plow through a whole bunch of work, we're going to say my upper bound is opposite x plus 1. What about my lower bound for y? That would be 0. And how about my x bounds? What would that be? From 0 to 1. I don't know about you, Wouldn't you guys much rather do this problem than have to break it up into 3 different cases? I mean, that gets to be kind of tedious. Not that it's super difficult, but well, look how much easier this is. Well, antiderivative of y with respect to y, of course, is what? Oh, y squared over 2, right? And then we're going to evaluate that between, like Pooh just said, 1 minus x if you'd like. And either way, you could put that in, 1 minus x or negative x plus 1, square it, all over 2. And hey, right now, we are virtually done. My goodness, we just have to finish this up. You know, foiling this out, and by the way, you can pull out a 1/2 immediately. If you FOIL this out, you have 1 minus 2x plus x squared dx. And just continuing this out, wow, we're almost done. Antiderivatives here all around, we'd say x minus x squared plus x cubed all over 3. And hey, it doesn't get much nicer than plugging in a 1 and a 0. Let's keep that 1/2 out in front. Plug in a 1, we get 1 minus 1 plus 1/3. Hey, these wipe out. 1/2 times 1/3, 1/6. Wow. Yeah, that's how you could evaluate that line integral. It would be equivalent to a double integral. Today, guys, the big idea is that your line integral will always be enclosing a boundary. It's like you're going around the perimeter of some enclosed shape. So real quickly, let's take a look at this next one. By the way, on your notes, do you have that little circle around the integral, that little ring? My apologies. When I printed that off at school, evidently we didn't have the font for that symbol. Could you just draw that in? And that in and of itself, guys, says, hey, don't worry about it. We've got positive normalization. Yeah, you don't have to worry. Sometimes they're saying, hey, we've got a circle. Are we going counterclockwise? Are we going clockwise? That could make a difference. If we're going clockwise, hey, we're not going to be able to work out Green's theorem. But, hey, rest assured, that's what we've got. So C is just this circle, my goodness. And then C, by the way, please do draw C in. Because, you know, guess what? We're dealing with line integrals today, of course, but ultimately we're going down to a double integral. And kids would say, hey, that's the path that this particle would be traveling around. That's our curve that we're integrating over. And here's our enclosed region. And real quickly, kids will say, hey, is it okay to do Green's theorem? And the answer, I hope, is a resounding yes. Positive orientation. It's a closed curve. Hey, we're good. Tell you what, let's say we're going to integrate over this region D. And let's see, I'm going to take my partial derivative of Q with respect to what? X. Then I'm going to take my partial derivative of P with respect to what? Y. Right? So up here's partial derivative of Q with respect to X minus partial derivative of P with respect to Y. Hey, these partial derivatives work out rather nicely. Let's see, what is that first partial derivative? What do we get? Just a 7. How about the second one? What do we get there? Just a 3. Wow. So this just becomes the the double integral of 4 dA. Okay, well, tell you what, if I had to integrate that, maybe we'll use polars. Okay, sadly, this video is going to wrap up right now, so we're going to have to pick it up for you guys in a bit.
That's the end of the show for